Good afternoon, everyone. My name's Joe Decarolis, and I'm the administrator of the Energy Information Administration. I just wanted to start by thanking you so much for taking the time to be with us today. We're really excited to tell you about Project BlueSky, which is focused on building EIA's next generation energy system model. We're going to get into the details in a second, but I just want to say on a personal note, as administrator with a background in energy modeling, how extremely important this effort is to me. Before we dive into the presentation, I want to just go through a few housekeeping items. You just heard the announcement that this is being recorded. So we are recording this webinar. It will be posted online after the event. All attendees are muted and you won't be able to share video during the webinar. However, if you have concerns about being recorded, please drop off the webinar at this time. There will be a Q&A period following the presentation. We're planning to present for a half an hour and then follow that with a half an hour for Q&A. You can submit your questions at any time using the chat function in the WebEx control panel. I also wanted to provide some high-level framing for today's webinar. As the project name implies, we want to be thinking blue sky today. We want to focus on what capabilities our next generation energy model should have, and we want to understand your unique perspective as an EIA stakeholder. I also wanted to call your attention. You'll see some information already in the chat box. It includes links to some YouTube videos that we've prepared that explain and introduce this modeling effort, as well as ways to reach us. And with that, I'm going to turn it over to Sauleh Siddiqui, EIA's chief modeler, who's leading Project BlueSky and is going to walk us through the presentation. Sauleh, over to you.
Thank you so much, Joe, for the introduction, and thank you also for the leadership and the inspiration. So I'm very excited to take you all through Project BlueSky, building EIA's next generation energy model. Next slide, please. EIA is the statistical and analytical agency within the U.S. Department of Energy and the nation's premier source of energy information. By law, our data, analyses, and forecasts are independent of approval by any other officer or employee of the U.S. government. Maintaining our independence and neutrality is an important aspect of what EIA does. You will see this theme in our goals for the next generation model as well. Our annual energy outlook explores long-term energy trends in the United States, and the International Energy Outlook explores long-term energy trends across the globe, both with projections to 2050. Next slide, please. Project BlueSky is a cross-team collaborative effort to consider EIA's future long-term modeling program. The goal is to build a next-generation energy model that would be used to produce our long-term projections, both for the Annual Energy Outlook and International Energy Outlook. We want to stress that Project BlueSky is not related to the updates we are making to the National Energy Modeling System, or NEMS, for AEO 2025. Those are short-term updates, while Project BlueSky is a parallel long-term effort. Next slide, please. The goals of the presentation today are to give you an overview of Project BlueSky, provide an overview of the desired model capabilities in the next generation model, clarify the timeline for this effort and next steps. In addition, we would like to receive your feedback on the following. As an EIA stakeholder, does this effort align with your needs? From your perspective, which issues are most important? How can we ensure an inclusive development process? Who else should we be speaking with? And what are we missing? Next slide, please. We want to motivate why we are rethinking our approach to long-term modeling. Three main reasons are highlighted here. First, the global energy system is changing rapidly. Technologies enter and leave the system at a fast pace. Low carbon and net zero pathways of increasing interest are coming through. Uncertainty in the energy system is heightened and increasing, resulting in risks to security, reliability, and resilience, which are evolving. Here, energy security refers to the uninterrupted availability of energy resources at an affordable price. Reliability measures the ability of a system to continue functioning. We have well-defined metrics for power systems, but not more widely. And resilience is the ability of a system to recover from shocks. Second, impacts on people are becoming more relevant and important. We have new policies coming in beyond market policies, such as industrial policy that has driven incentives for energy communities and local economies. The infrastructure changes associated with the energy transition have material impacts at the regional, community, and household levels. And then third, the world is becoming increasingly interconnected. Electrification has increased interconnection between both energy and non-energy sectors. The global growth of renewables and batteries draw on the same material supply chains, interconnecting our economies further. And finally, feedbacks to the energy system from macroeconomic and international trade are becoming more relevant to the energy system and to the models that represent it. Next slide, please. Given how the energy system is evolving, there's a need to think beyond our existing long-term models. On the top right, you see an excerpt from the Infrastructure Investment and Jobs Act of 2021, also known as the Bipartisan Infrastructure Law, that asks us to strive to migrate towards a single, consistent, and open source energy modeling platform. Within EIA, we have also been thinking about this much before this legislation, through internal studies and reports. Specifically, we have been using the National Energy Modeling System, or NEMS, to produce the Annual Energy Outlook since 1994. The code base has become unwieldy and difficult to maintain. Both inside and outside EIA, there is a broad recognition that we need to develop a new modeling framework. Next slide. Now that we have given you some background for why we are rethinking our approach to long-term modeling, we want to take you through what we are planning to do for developing the next generation energy model at EIA. Next slide, please. One way to conceptualize energy models is to think of them as 4 representative layers. The governing dynamics are the methods used to drive system changes over time. You can think of these as policies, markets, and technology evolution that impact the system. The mathematical representation of these governing dynamics are equations used to represent the evolution of the system. The code implementation represents the mathematical formulation in terms of a programming language that can be used in computation. And finally, the model output is equally important for visualizing output and explaining the assumptions, context, and insights pertaining to the model. We want to stress that Project BlueSky focuses on reevaluating all 4 layers of our models. Next slide, please. Unfolding the 3 motivating factors of how the energy system is evolving on the left, the 3 goals on the right outline our goals for the next generation model. We want our model to be open and accessible, which means the source code and input data should be available under a permissive open source license. We want our model to be nimble, which means update and change quickly, flexible, so it can handle diverse modeling needs, adjust model complexity to suit the question, and separate the code and data, and modular, so it can have a detailed system representation while making it easier to swap capabilities depending on the task. Finally, we want our model to be capable of performing robust and granular analysis. This means a rigorous consideration of uncertainty to quantify resilience, reliability, and community impact. Next slide, please. We believe an open and accessible model will help promote transparency in our work, an important part of EIA's mission, enable model introspection and clear misconception about our analyses, validate and receive feedback on new and existing approaches, allow replication and expansion of our model-based analyses by you all and others, collaborate on model development in a way that aligns with our mission of being independent. Next slide. We also plan on using modern software tools and programming language. Modern open source software is free with a large community of users and amenable to future needs, for example, using it in the cloud. It's able to handle new types of math formulations for emerging issues and to communicate with different modeling languages to automate processes. It can handle large data needs of pre-processing, organizing, analyzing, and validating data. And we will have access to both an external talent pool and internal staff experience. Next slide. There's a host of reasons why we need a nimble, flexible, and modular structure. Technology innovation is rapid and evolving, and we need models that can match this pace. The ongoing shift to renewables requires a high degree of spatiotemporal detail, which needs to be flexibly balanced with model complexity. The policy environment is evolving, with recent focus on targeted incentives for communities and economies. Rapid energy system changes impact people in new ways, different from before, both from policies and infrastructure that are distributed and interconnected. This environment heightens uncertainty in decision-making and requires us to incorporate that uncertainty in our modeling. Addressing this complexity requires a model that is nimble, that can be updated or changed quickly, flexible, that can handle diverse modeling needs, and modular, that allows us to swap model components depending on need. We want to emphasize that a nimble, flexible, and modular, oh, can we stay on the previous slide, please? Thank you. We want to emphasize here, before we leave this slide, that a nimble, flexible, and modular model helps us collaborate with stakeholders and allows them to update the model on their end as needed. This furthers our mission of being transparent and collaborative as we take on future challenges of energy system modeling. Next slide, please. First, let's outline why we need robust analysis. On the right, you can see the National Research Council in 1992 stated in a report that uncertainty is inherent in the nature of models and cannot be eliminated, nor should it be ignored. They advise that NIMs should be designed to represent and analyze the effects of uncertainty explicitly. We know that energy advancements are moving at a faster rate than available data, especially for new technologies and policy. Thus, quantifying uncertainty must be foundational to the assessment of energy future. Uncertainty analysis allows us to more accurately reflect what we know about the future. An example of how we have already strived for this is shown below from the 2023 annual energy outlook. The graphic shows total US energy-related CO2 emissions as output from NEMS. The black line is the reference case, and the gray lines are the most extreme side cases. The dark and light blue shaded regions show uncertainty ranges for the future projections based on past differences of our projections with actual outcomes. This provides more context beyond our side cases for the uncertainty inherent in our analyses based on past performances. While this was a first step in addressing uncertainty in our AEO projections, our next generation model will move beyond this effort to further endogenize uncertainty and provide a robust analysis of our projections. Next slide. In terms of granular analysis, we see a need for more details within space, time, and people. Wind and solar, for example, are growing at a rapid rate. Simplified modeling could assume away operational issues in capacity modeling, but we can't because capacity deployment decisions are affected by the economics of operation. Thus, we need to characterize resource variability at much finer scales. We also need long time series records, hourly resolution over multiple decades to ensure resource adequacy in systems with high penetration of renewables. If you look at the top right figure, it shows wind variability by region over the course of a year. While some regions, such as the lower and upper plains, have yearly variability close to the US national average, other regions, such as the West Coast, show an opposite trend. The bottom right figure shows the changing duck curve in California. The duck curve measures net load, remaining load after solar is subtracted. That net load requires fast ramping capacity that poses operational challenges that need to be modeled at a granular temporal scale. Among all these changes, we want to quantify the impacts on people with a higher spatial resolution as well. People are affected by changing infrastructure through local changes to physical infrastructure, availability of new consumer technology, prices affecting energy burdens, shifts in energy-related jobs. Understanding how different communities are impacted by changes in the energy system and how they will feed back into its evolution is essential for our next generation. Next slide. I will now hand it over to Joe to talk about how we plan on expanding model boundaries in the next generation model.
All right, thanks, Wally. In this section of the presentation, I just wanted to provide some indication of how we can expand the modeling boundaries beyond our current capabilities. I'm going to step through some options that represent a progressive expansion of our current modeling boundaries. And these are really meant to be illustrative There's lots and lots of different possibilities, and I'm hoping that the Q&A can draw out some additional ideas and directions. Next slide. I wanted to start by just talking about where we are right now with something like our annual energy outlook, which is one of our highest visibility, flagship products. And in the annual energy outlook, we run a limited number of cases, and we produce outputs like capacity builds, energy production and consumption, CO2 emissions, and then some price information. So if you look at the figures at the right, the one on the top is showing installed capacity in the electric sector in 2050 across all of the cases that we model. The bottom is showing the range across the cases that we ran in petroleum consumption and production. So again, this is illustrative of the kind of information that we present from our long-term modeling efforts. Next slide. So if we think about how we can start to expand the system boundaries beyond where we are right now, a first step might be to model conventional fuels and changing trade patterns and how they affect security, reliability, and resiliency, as Sauleh laid out. So we know that there are changing trade patterns. The geopolitical risks associated with conventional fuels are complex, and it would be really nice to be able to model a wider range of scenarios that included fuel price shocks. Just a couple examples here on the top right. This is showing the destinations for US exports of liquefied natural gas, or LNG. And what you can see is that there was a big shift from 2021 to 2022 from Asia to Europe. And this shift was basically due to Russia's full-scale invasion of Ukraine and a shift in exports from Asia to the European market. The other thing I'll mention is that LNG exports from the United States began in 2016. We are now the largest exporter of LNG in the world. So again, a very dynamic market. Another example that I think is interesting is the bottom stacked bar graph is showing sources of uranium that feed the light water reactor fleet in the United States. And most of that uranium is coming from international sources. There's only a very small part of it that's mined domestically. So, we track this data and we do model trade to some degree, but we don't model these trade flows endogenously in a detailed way in our current modeling work. And this would represent one expansion of our current modeling work. Next slide. We can go a bit further and extend our capabilities to consider critical minerals, which we don't currently model. This is a really important topic. There's obviously a lot of talk about it, and it's something that we're already working with the U.S. Geologic Survey on. Critical minerals represent new and evolving supply chain risks. We know that batteries and renewables are growing quickly, and they rely on several critical minerals. And then finally, recent policy, including the Inflation Reduction Act, incentivized domestic production of critical minerals, so it's important to be able to model them. The figures here are drawn from the International Energy Agency. On the top left, we have critical mineral requirements for EVs and for conventional vehicles. The top bar is EVs, and you can see that there's significantly higher critical mineral demands for those vehicles, including copper, nickel, manganese, cobalt, and graphite. And then on the top right, that's showing critical mineral requirements for various electric generating technologies. Renewables are on the top. They have the highest critical mineral requirements, and they're also growing the fastest. On the bottom, this is also a figure that's drawn from the IEA, and it's showing the location of copper and lithium mines around the world. But what they've done is superimposed water stress levels on top of the locations of those mines, and it just sort of shows the intersection of these critical challenges, locating these minerals and the fact that there are high water requirements for processing these minerals. Next slide. We also want to be able to consider infrastructure development in a more detailed way. As the energy transition proceeds, we're seeing significant turnover in infrastructure. So we want to know what's being retired, what infrastructure is being added. If you look at the maps on the right-hand side, the top one is showing the US natural gas pipeline network. On the bottom, it's showing planned capacity additions by location in the US electric power sector through the end of next year. Again, this is information that we track, and we want to be able to build it into our next generation modeling effort in a more with more granular detail. If we could do that, it would allow us to better characterize the effects of federal, regional, and state level policy. And by understanding those changes in infrastructure in a more detailed way, it also helps us understand impacts on community well-being. As Sauleh indicated, it would also provide some information about potential locational shifts in energy jobs, and it would inform regional assessments of security, reliability, and resilience. Next slide. And then finally, we want to be able to consider the impacts on people in this next generation framework. I want to start by talking a little bit about our Residential Energy Consumption Survey, or RECS. The latest version of that survey, we were able to collect 18,000 different household observations, and that's allowed us to produce statistically significant results at the state level for the first time. If you look at the top graph, that bar graph, it's showing energy expenditures in dollars per square foot across different demographic characteristics like ethnicity, race, and household income level. The bottom graphic is drawn from a new RECS dashboard that we've developed and is available on our website. This particular snapshot is looking at air conditioning consumption per household. You can see the darker colors there in the southern United States are indicating higher AC load. The idea is, again, we have a detailed understanding of energy consumption at the household level. Can we apply statistical methods to project this into the future? So not only aggregate energy demand, but these demographic characteristics as well. That would help provide more clarity on the effects of policy that targets specific communities or households. So again, in the IRA, there are bonus provisions for energy communities. This sort of representation would help us understand the impacts of policy like the IRA. It would also help us determine who benefits from new consumer technologies that are incentivized by policy. And it would also help us evaluate evolving household energy burdens and vulnerabilities, which are going to change as households adopt different fuels and new technologies. So again, these are just some examples of directions that we can go in the next generation framework. They're meant to be illustrative, and I'm hoping in the Q&A we'll be able to discuss some additional ideas. Next slide. And I'm gonna turn it over to Sauleh to talk about next steps with this effort.
Thanks so much, Joe. So what's next for the next generation modeling effort? Next slide, please. So we'll have continuous outreach and feedback with diverse stakeholders like you all via individual conversations, focus groups, webinars, and at conferences. The next year will be spent building a basic prototype of this model and testing its capabilities. The goal is to release a prototype publicly via GitHub and an open source permissive license by this time next year. We want to stress that the prototype won't have all the capabilities outlined here and also won't cover the entire energy system as NEMS does, but it'll form the basis of a flexible structure for which new capabilities will be added. We want to stress that this work is tough and it's cutting edge, but we strongly believe it's collaborative. That is why we're focusing on continuous release and updates and getting continuous feedback from you all, not a final product that we simply deliver. And so we hope that you collaborate with us on this effort. Depending on what we learn from the prototype and how feedback goes, another 2 years after that will be dedicated to further model development. And then eventually we plan on using the next generation model to produce the annual energy outlook and the international energy outlook. Next slide, please. So in conclusion, rapid changes across the energy system require us to continually adapt our modeling approaches. We need to make our work more collaborative and accessible, something that this initiative strives to do. But we also need to leverage and build on existing work and open source ecosystem, both inside EIA and outside of EIA. So with that, we'll now answer some questions that have been posted in the chat. Please continue to post questions, and then we'll be able to get to them as we can. Joe, thanks for turning your camera on as well. And I'll start with reading some questions, and then we can slowly take them one by one. So the first question we received is, I've been deploying NEMs in academia for 11 years, and in that time, the vendor who produces the bespoke US macroeconomic model for NEMs has changed hand repeatedly, and its cost has more than doubled to 25,000. In Project BlueSky, will EIA avoid using vendor products that drive up the cost of independent instances of the resulting modeling system? So I don't want to, I'm gonna answer this question in a much broad way, and then because this is applicable to a number of things. It's not just applicable to the macroeconomic model we use, but also applicable to other types of vendor products, such as data products, as well as the type of solvers that are used to solve the model as well. So we intend to make this model open source and accessible with a permissive open source license. That doesn't necessarily equate it to meaning that every product that is used to run the next generation model will also be free and freely available. There's a number of reasons for that. Part of it has to do with the data products we use. Some of them are proprietary. Another part of it has to do with EIA's mission. And then the third part is there's capabilities that EIA doesn't have internally, such as the development of solvers, or in this case, as you're pointing out, the macroeconomic model. There's some things that we do not have the resources and capabilities about. However, I do want to point out that thinking about how we model the macroeconomy is part of Project BlueSky, and so we are thinking about how can the model work either with our current macroeconomic model or as a hybrid version of it, or even if we need to replace it, what that could look like. We haven't made a decision about it yet. What I will tell you is we're striving to make this open and accessible as much as possible. So one way to think about it is this is another advantage of the modular structure, that even eventually, if there are components of this model that you do not want to pay for, we want to make sure it's modular in a way so that you can swap those out for components that are more easily available to you, for example. And we're also hoping that we can release it to be flexible enough so there's a version enough that can also be accessible to folks that might not have the computing capabilities or data capabilities that are needed. So while you might not be able to exactly replicate by yourself everything that EIA does because some of these limitations that we have, we're hoping that we can make it as easy and as close as possible to that as much as.
I mean, if I could just jump in, Sauleh, I would say, as a design principle, our first objective is going to be to try and make it open source. So with regard to the macro model, that's certainly something we would look at can we build our own open source macro model, or is there a version that exists that we could use? And then I think, as Sauleh was describing, there's sort of a trade-off there. So if we find that there really is no good way to substitute, a proprietary model, we might include it in our framework. But even in a case like that, because it's modular, we would design it in a way where one could substitute that module out and then replace it with something else. But the design, the priority for design is to try and identify open source solutions.
Thanks, Joe. I will now go to the next question. Is this new model, will it be packaged software or just code? What programming language are you planning to use for the new model? So we intend to make the code the code available as a permissive open source license. So we're gonna, as much as we're not using proprietary software or anything else within our model, we will make that available. Anything that we develop that isn't proprietary, so that'll be available for you to change. And like Joe said, we're trying our best to use as many open source and accessible programming languages as possible. What programming language are you planning to use in the new model? We're actually exploring that right now. We're testing out a host of languages to see which one is most applicable to our model. This includes thinking through Python, but it also includes modeling languages that aren't necessarily free, because if they provide speed and flexibility that we otherwise have, then we want to make sure we keep those options open. But as Joe said, we're going to try our best to use open source and accessible programming languages that are widely used, as we pointed out in the slides as well. That opens us up to more collaboration. It also opens us up to also an external and internal talent pool as well. Joe, did you want to add anything?
No, I think you said it nicely. There's the open source code, and then again, to this question, and also relates to the first question. We're also trying to use, to the degree possible, an open source software stack. Again, that minimizes the barriers to entry. We don't want to have to pay for expensive software if we don't have to. We don't want other people to. There are some cases, I'm sure, if there are modelers on the line, they're familiar with commercial solvers that you need to solve optimization problems. That's an area where it can be hard to get around good commercial solutions. But again, a design principle is to try and employ, not only make the code open, but to use an open source software stack where we can. So using languages like Python.
Thanks, Joe. We'll go to our next question now. For the next generation of energy systems models, are you thinking about how to adapt or redesign such models to incorporate climate change projections, ensuring that the potential climate impacts on the performance and reliability of renewable energy sources like solar and wind are adequately considered? I'll answer this in a general way again. So for this particular example, and sort of in general, and this is an example of something that we know is becoming more and more important to the energy system. In terms of climate change impacts, in terms of macroeconomic impacts, international trade. And one of the reasons why we want to be able to build a flexible model that can handle these diverse needs is exactly this. So while there's a number of things that we want to be able to include, one of the things we know is that being able to have a system that can flexibly include these allows us to focus on including a host and a list of things. So rather than taking a piecemeal approach where we're looking at specific examples and saying, is this included, yes or no, is it included, yes or no, we're looking at the full suite of examples and then seeing how can we make our model flexible enough. So if we did need to add these, it would make it easy for us to do so. And so that's one aspect of this, is that yes, the answer is yes. Is this specifically something you'll see in the prototype? Probably not, but in the prototype, one of the things we'd love feedback on is the prototype developed in a way that we could add the capability that you mentioned. And I would point this out for any capabilities that people are asking in the chat about, is that we want to think about this model in a way that we want to make it flexible in a way so that those can be added, and not just added by us. This is also something we want the community to also consider for their own needs, right? Like if they need to add a particular capability, we want to be able to deliver a model that you're able to do it as well.
I guess I'll just add, I think this is a good example of another direction in which we could expand the model boundaries. I mean, as I understand it now, we do project demand into the future, and part of that relies on, temperature projection. So there's some we're taking into account, temperature trends that include climate change over the last couple of decades. But there's lots of other ways in which climate can impact supply and demand, and I think that's something that it's a good example of another way in which we can expand system boundaries, and I think that's a good example.
Thanks, Joe. So the next question: modeling emerging seasonal storage technology, including iron air batteries and hydrogen, requires a high level of temporal resolution to capture accurately. This is often left out in many current models in the name of computational tractability, meaning that these important technologies are often not captured. What are your thoughts on how Project BlueSky might be able to address this need and the attendant computational trade-offs? So this is again a really good question in terms of again different types of new energy technologies that are developing that often require either more computational capability or the flexibility to be able to do that. So one of the things that we want to be able to do with Project BlueSky is to take technologies such as iron air batteries and hydrogen and understand, could we create a flexible enough model so that it could increase that temporal resolution while remaining computationally tractable. Now, that'll require some type of trade-off, right? Like you won't be able to run, even with all the computational resources, something that is at a very granular level of detail with all the technologies built in. But we want to make the model flexible enough so that if this does need to be the focus, it can be modified in a relatively easy way so that you are able to run as close as possible as the granularity required for this. But to answer your question, yes, thinking about temporal granularity is at the forefront of how we're thinking about it, and building that flexibility in from the very beginning is also how we're approaching this problem. And so we're hoping that the computational and granular trade-offs that need to be made can be made by the user as opposed to being attached to the model that the user is using. Next question, thoughts on how much data and representation you'll include for Canada and Mexico. Again, this is, so we have both a domestic model, which is NEMS, National Energy Modeling System, and an international model, which is the World Energy Projection System. This effort focuses more on advancing the modeling aspect of it, so that if there is a need for more data and representation in international countries or domestic, we're able to flexibly add that. The specific data collection isn't necessarily part of Project BlueSky. That doesn't mean that it's not also something that EIA is doing in another part of the work that EIA does.
Well, if I could just jump in with just kind of like a design, concept, and it kind of relates to the regional representation. If the next generation model is ultimately going to be used to produce both the annual and the international energy outlook, it kind of gets back to this idea of flexibility and modularity. So if the model is designed, in a modular way, it might be that when we run the AEO, we have a more coarse-grained representation of the rest of the world, but in a way that still allows us to capture endogenous feedbacks. But more of the detail would be, on the U.S. domestic markets. When we model internationally, we might want to back off the detail in the United States and increase the detail in the rest of the world. And again, the idea is if it's modular, you can basically craft the input data for the analysis that you're trying to perform. So again, with Canada and Mexico, there might be a particular series of questions where we really want to understand trade flows within North America, and so there is a version of the model and the data we use to answer that question. Again, to Sauleh's point, it wouldn't have a sort of a fixed resolution that you're locked into.
Thanks for adding on. And actually, this next question is related to this conversation we're having. Is wondering how nimble and flexible can go hand in hand with the complexity of the issues you described. Absolutely, right? Like I think, how can we say that we can create a nimble and flexible model, given that the energy complexities we're dealing with are so complex that it might be difficult to make it nimble and flexible? Well, the one thing I'll answer with this is I think internally at EIA, we do believe that there's a possibility to try for this, because we also think this is an important path forward for energy modeling. Energy modeling traditionally haven't been being built with this nimbleness and flexibility, and rightly so. There have been different models that handle different parts of the complexity of the energy system. So we're trying to be able to build our models to be nimble and flexible like this. And in fact, one of the things I'll say is that even our current models tend to be nimble and flexible in many ways, that we believe that this is possible. For example, the current structure of NEMS is modular. That has allowed us to actually update different modules one by one, as opposed to require and keeping the details and the complexity of individual sectors inside NEMS. And it allows us to update the model one by one, as opposed to trying to update it all at the same time. It also allows all our different modules to have different spatial and temporal granularities. And so I think the two reasons to believe this is, one, I believe that this is an absolute need, and we should at least try to see how far we can get into making this nimble and flexible. But at the same time, I think we have a lot of really good internal expertise in making some aspects of this happen really well. And so we intend to utilize that expertise as much as we can in trying to also structure this next generation model. So the next question. Very excited that you will be representing a wider set of uncertainties in the next version of the model. Any chance the uncertainties represented could include key uncertainties related to climate and health, uncertainty about leakage rates of methane from gas infrastructure, uncertainty about permanence of CO2 storage, bounds on levels of local pollution associated with different types of energy use? So the idea, and again, we are still testing exactly how we're going to include uncertainties. There's a lot of different methods available to us, and when we're also looking internally at what methods we can use to address uncertainty. I will tell you, though, that any type of uncertainty method that we pick we're going to try and ensure that that method can be applicable to a number of different types of parameters and variables that we want to attach that uncertainty around. So, for example, while in a future energy outlook, EIA might not necessarily deal with all the uncertainties that you listed here. What we want to be able to do is, if we do need to deal with them, we want to be able to change our model relatively quickly, make it flexible and nimble enough so that we can change it and address that uncertainty in a particular model output. So again, and it's the same thing with all of you all out there, right? Like we understand that, given our priorities, given our mission, we won't be able to address every single question out there. We need a community of modelers like you all that can help answer questions. But what we want to be able to provide is a collaborative framework where you can take this and say, well, okay, even if EIA didn't address the specific topic, at least I have a model that I can then use and modify and try and address that topic as well.
One thing I just want to jump in with is the way that we're thinking about a next generation model at EIA, just in terms of some of the specific things that were mentioned in the question. We want to keep this focused on being an energy systems model. So I don't foresee this turning into, an integrated assessment model where we're looking at, for example, health impacts. I think that gets beyond EIA's mission. But if we develop an open source energy systems model and other organizations or individuals would find that useful, of course, it's open source, so they can take the model and do that analysis. So we're very much thinking about this as an energy systems model. Again, we're talking about expanding the boundaries in some ways, but I think we're trying to keep it focused on energy.
Thanks. I'm going to combine the next two questions, which is, how do we deal with confidential data, and what is the significance of explicitly attaching a permissive open source licensed EIA code when government publications, presumably including code, are already public domain? So this is something we're actually looking very deeply into. And Joe, I'm gonna start off the answer, and then please add on to it as needed. But this governance structure for us as a government agency, as well as the exact type of license we're going to use and how we're going to deal with confidentiality and other types of proprietary information that we have, that's something we're looking into. And we believe that there are particular license structures that we can move forward with. So Joe, I'll hand it over to you, since you know about this area a little bit more than I want to add anything.
So first of all, when you have an open source license, first of all, you want to choose one that's well recognized, because there's very little case law in this area. So you don't want to, in my opinion, it's not a good idea to just create your own custom license. So we're looking at, well understood open source licenses like MIT and Apache 2.0. Those types of licenses do a couple things. First of all, there's a disclaimer that basically says there's no implied warranty with this product, right? Like you get it as is. The other thing is that it clarifies copy and patent rights. And the questioner is right that government products with the vast majority of government products tend to waive copyright, but it's not clear that copyright waiver applies overseas. So if someone in Europe, for example, were to take our code, our model code, and use it, that government copyright waiver it's not clear that it would apply. So by applying an open source license, you just take that issue off the table, because you make a very clear statement about copyright and patent rights.
Thanks so much, Joe. All right, next question. We have a lot of questions, and my apologies if we're not able to get to all of them. We will be putting up an information on how to continue to reach out to us and how to continue to get more information. But we'll keep going through these questions with the time we have. Could EIA create toy models for proprietary components, things that allow users to have the full featured model, but without the same level of precision or accuracy that is expected out of EIA's analysis? So first thing, we definitely want to be able to develop the model in a way so that if a toy component needs to get added, it is easily added in. And that toy component can be something that either we develop, or something that someone else has developed that can be easily added in. So yes, that's one goal of creating a modular framework, is so that you can attach toy components or representative components there if you do not want the full detail of that components. Are we going to be responsible for creating every toy component for every proprietary component? That's not something we've made a decision on yet, but I can tell you that we want to make it so that you're able to run our models and use our models as easily as possible. So I'm hoping at a very basic level, you're at least able to run it without the proprietary components. And if we're going to create toy components of that, that's something we still have to decide and see how much effort and stuff we can put into that.
One thing I'll say is, to be clear about the effort is, we're going to design the framework in a way that we think meets our needs and the analysis needs, of our stakeholders. So we're not going to be necessarily designing it in the perfect way for stakeholders that actually want to pick up the model and use it. That said, I do think that there's a lot of overlap between our interests and what we're trying to accomplish with our analysis and what our stakeholders are going to be interested in. And one thing I've been thinking through some of these questions that maybe it helps as an example is, if you're familiar with climate modeling, and you use the general circulation models, the big 3D models of the climate, there are various ways that you can, configurations with which you can run those models. So for example, if you look at the ocean, you can run the model with prescribed sea surface temperature. So you basically don't model the ocean at all. It's just there's a sinusoidal wave which represents sea surface temperature response. Or you could model an interactive ocean with the full 3D representation, but you need a lot more compute cycles to be able to do that. And which version of the ocean you choose to run depends on the question that you're trying to answer. And I think there's a nice analogy there for energy models. We don't always want to run the most sophisticated version of every module for every analysis or every question that we're trying to answer. So I kind of see having, developing different versions of modules that can plug in. And again, that is very much going to be guided by the analysis that we intend to do. And then whatever we develop, we would provide to stakeholders. So hopefully that helps a little bit just in terms of how we're thinking about it. But as Sauleh indicated, there's still a lot of details to sort out.
Thanks. And so this next question also kind of related, moving on from that. I know you mentioned you're going to release a publicly available prototype sometime next year. Are you considering doing development of the prototype openly as well? It would be easier to learn what you are doing, provide feedback earlier on in the process that way. So one thing I want to stress is, first, the prototype will be at an incredibly basic level. So I think I just want to manage expectations that the prototype you'll see next year won't be a fully developed energy model. It will in fact be at an early stage so that you all can give feedback. So that development of the prototype, for us to come up with something, given the tests we're doing internally right now and the structures we need to develop and making sure that it meets the needs of EIA, that time will take us about a year to do. But as soon as we put it out there, that's when, that is the prototype development. That prototype development will move on after that. And so we're hoping that over the course of the next year, when we go through some internal decisions and testing and figure out what that would be like, we do plan on having an open process of how we're going with this. The other thing I want to stress, though, is that I think one of the things that is important at EIA is that one of our first efforts was to look at the other open source models out there and other models out there. We are not interested in recreating the wheel. We want to be able to use external and internal information that we have. The reason we're building a new model is we believe that the capabilities that we outlined here, the nimbleness, the flexibility, the modeling on uncertainty, open and accessible, all of those aren't available in any single modeling framework. But we want to be able to use as much information out there as possible. But to do that, we also want to make sure that we understand that whatever technology and new type of software and stuff we're using is something that can also work for EIA in the long run. So developing this internally allows us to also really understand that it'll meet our needs, but also it helps us utilize our internal talent pool and keep that idea and that information with us as we move forward. So definitely this is a collaborative process. The prototype won't be a final model without any input. That is meant to be, you can think of this as the beginning of the conversation. And this is why we're coming out right now, to make sure that you all are prepared. And if you all have, advice or like any other things, information you would like to provide to us, we're always open for input as well.
The other thing I'll say too is that we really want to leverage, modern code development practices. So we're thinking very much about using a modern language, as Sauleh indicated, like Python, being very careful about code documentation so that you can take a very simple version of a module that will, hopefully will release next year and actually pick it up and run with it and, be able to work with it. And I think in the interim, as we're kind of building that initial prototype, there's still going to be outreach opportunities where we're trying to think through, specific issues, whether it's respect to data or algorithms, where we'll be having a series of meetings. So there's going to be plenty of time over the next year to provide input. And then once we do release an initial version of code, the goal is that you can pick it up and understand it and run with it.
Thank you. So next questions. Do you plan to use one model for both AEO and IEO projections instead of the current NEMS and WEPS Plus? Again, I think that is a decision that we still have to make depending on how this prototype develops. But I will say that we want, as Joe already answered this earlier, we want it to be flexible enough that we can at least have a base framework that can then be adapted to international and domestic analyses. If that eventually turns into two different models, that's fine. If it stays one model, that's also okay, but that's not a decision that we've explicitly made yet. Right now, we're just trying to get the basic structure set up. Joe, did you have anything else to add to that?
Yeah, I guess just as I think about it, as a modeler, it's hard to just isolate the United States, right? And then it's hard to, model internationally without a good representation of the United States. I mean, everything, we want to be able to capture key trade-offs endogenously. So I do think it makes sense to have a model that can capture both the international issues as well as the domestic issues in more detail. But as Sauleh said, I mean, there's a lot to figure out. We don't exactly know how it'll end up, but that's something we're thinking about.
The next question is also kind of related. Will you still keep the short-term energy outlook STIO modeling separate from medium and long-term modeling, and just keep benchmarking to an ongoing STIO? Again, that's a decision we have to make, as we move forward, and that's something that's an overall sort of EIA decision. This is focused on long-term modeling, but that does not mean that we're not considering the flexibility and the capability of being able to use short-term or even doing short-term projections. Joe,
I will, but I will clarify. I just want to be very, very clear. Nothing changes with the short-term energy outlook. So that's like a separate econometric model. And so, there will be no change to the STIO based on, this next generation model, as Sauleh indicated, informs our long-term modeling, not our short-term. Now, in the very long run, do we learn things from this effort that could inform a short-term energy outlook? Perhaps, but right now that is not part of this effort. STIO is its own thing.
Thanks for clarifying that, Joe. And then we had a host of questions, and I'm not going to read all of them, but there's a host of questions about, will the new model be more comprehensive in terms of emissions, for example, from the agricultural sector, system impact household, future vehicle types, spatial granularity, projections beyond 2050, macroeconomy, et cetera, et cetera, et cetera. And again, you just want to stress that what we want to be able to do is, we want to be able to add the relevant aspects of the energy system to our long-term models. And we want to ensure with the next generation model is that the model isn't the impediment of adding the things that we think are necessary. So we're trying to make the modeling aspect as easy as possible in terms of trying to add any level of detail that EIA deems necessary that it needs to be a part of in its long-term projections. And again, if there's something that EIA doesn't deem necessary going forward, another reason why we want to make it open and accessible is that we want to make it easy for others to add to this as well. So with that, we're actually almost approaching time, and if we could go to the next slide, I'll take the last question with the next slide that we have. Oh, and this slide, actually, we can go back to the previous slide. Thank you. But there's a question about what's the best way to stay informed of progress and of opportunities to give feedback? Is there a specific mailing list? Also, would it be possible to share the slides for this presentation? So if I can ask one of my co-panelists if they can put the email address where people can reach out to us in the chat. So we have a specific dedicated email inbox, next generation model at eia.gov, and you can reach us through that. You're welcome to email us at that address. That address will be monitored, and that's one way that we'll be communicating and taking input in from you all. And stay informed of progress and opportunities. We're planning on having more public events like this as we move forward. We're also going to have a web page that'll have a recording of this webinar, a recording, links to the 2 videos that were also placed in the chat, as well as a link to these slides so that they're available. So all of that information will be put over there on our website as well. And we'll be providing updates on it as we move forward. But in the meantime, you all are really welcome to please do reach out to us. You know, if you registered for this webinar, you're already on our list for providing updates. So we will ensure that as updates come in, we'll definitely reach out to you all. And so we're hoping that as we develop that webpage and resources, as things come up, we'll keep you posted by email. And then we'll also use our regular channels of our website, social media, to keep folks updated as well. So with that, I do want us to go to the last slide now. And I want to thank you all for engaging so robustly. We have written down all the questions you've given us, and we're hoping to answer them in the future. But I will, you know, with this gratefulness from me in terms of like with all the questions you all have and the engagement, we're very excited about this. I will hand this over to Joe.
Okay, thanks, Sauleh. I just wanted to echo your thanks. I just want to thank everybody for tuning in. You know, it looks like we had over 350 participants. The questions were great. The thing I want to emphasize is that this is a really big and also important undertaking. It's a really exciting opportunity to, you know, fundamentally rethink our long-term modeling program. And I just want to emphasize that we want to remain engaged with the broader community. This is just the very first step in that. So do please continue to engage with us. I think the very next step is, as Sauleh indicated, we do have the list of registrations for this webinar. Once that webpage is with the next generation modeling information is ready, we will email the list so that you're aware of it. You can access those materials. And then if you have specific questions or requests, again, use that next generation email address that's provided in the chat to get in touch with us. Follow us on social media. And again, thank you very much for your time. And we look forward to engaging with you on this important topic in the future.